Precalculus lesson 11.3. The number e is 11.3. The number e. This one should be fairly quick. There's just a little bit of concept and a couple new formulas for you. Number e, the e, we call it Euler's number now. So e, hold on a second, that is with one L, right? I'm suddenly drawing a blank here. Euler's number. Yeah. I don't know why I was like, sure, if I just finished writing, it would have been like, yeah, that looks right with one L. Euler's number. It looks like Euler, but the guy was Swiss, Leonhard Euler. In Swiss, the EU makes the oi sound, not the u sound. Kind of like interesting little tidbit. Dr. Seuss, we have that same EU. He was Swiss. Theodor Seuss, Giesel was his name. And when he started writing by Dr. Seuss, he was pronouncing this middle name like his name would be pronounced in Swiss, and it was Dr. Seuss. And he had some kind of rhyme with that, I forget. The Dr. Seuss like rhymes with noise, not whatever. But yeah, it was originally Dr. Seuss, and then but people who didn't know the Swiss background and how to pronounce it kept calling him Dr. Seuss, and it drove him crazy for a while. And he kept trying to correct people. It was like, no, it's Dr. Seuss. But finally, he realized, you know what, this is a lost battle. Okay, I'll just embrace it. And at least Dr. Seuss kind of sounds like Mother Goose. It kind of has a nursery rhyme, children's kind of feel to it. So we went with it. But anyway, Euler was an 18th century Swiss mathematician. And he did some initial work and discovery with this number. And then later, Bernoulli did some work demonstrating the applications to some other things. Anyway, there's some noise out there. I was just seeing what was going on. Yeah, Euler's number. It's approximately 2.71828, and it keeps going forever. Like pi, it's an irrational number. It keeps going forever. Yeah. Well, it turns out it shows up all over the place. So especially if you get into any calculus, the number e starts showing up all over the place because of what happens with certain types of equations and their derivatives or their integrals have the number e show up all over the place. But a couple ways of representing it. The number e can be represented as the limit as n approaches infinity of 1 plus 1 over n to the nth. In other words, as n gets infinitely, approaches, keeps increasing without bound, it gets bigger, 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 bigger. We have 1 plus 1 over an infinitely large number. This is getting closer and closer to being 1 plus 0, but not quite, but it's getting closer and closer to being 1 plus 0 to an infinitely large exponent, to an infinitely large power, and it just ends up being that as n approaches infinity there and approaches infinity there, the number that you get closer and closer and closer and closer and closer to is the finite number e, is this irrational number 2.718281828, etc. It's not a repeating it. The pattern changes. Another way of representing it, though, is it could also re-represent as the sum. Now, I know we haven't covered these yet, but we'll get into it. The sum, we'll say from n equals 0 to infinity of 1 over n factorial. We also haven't technically gotten into factorials yet, but maybe you did a little bit of them in Algebra 2. But this would be 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus dot, dot, dot. 0 factorial, we'll talk about this later, is 1. So you have 1 plus 1 factorial is also 1. So 1 over 1 is 1 plus 1 over 1 is 1. So you get 1 plus 1 plus 2, or 1 half, plus 1 over 3 factorial. 3 factorial is 3 times 2 times 1. So that'll be 1/6. And when you keep this going forever, you end up getting infinitely closer and closer and closer and closer and closer to being exactly E. So a couple ways that it comes up. It turns out if we took compound interest, because let's see, compound interest, recall compound, well, I'll say exponential growth. Exponential growth. What did we have? Growth. What did we have? We had n equals n sub 0 times 1 plus r to the t, right? Okay. Or exponential growth, how about our compound interest? Compound interest. We had a equals p times 1 plus r over n to the n t. Notice we have some similarities going on here, where if you had r as 1, 100% interest, which I would take any day, no, that'd be sweet, 100% interest divided by, well, here we're an infinite number of compound interest per year times that same infinite number of time intervals. Is basically, if you, it's like, what would happen to your growth if you took $1 and invested it at 100% interest, not compounded monthly, not compounded weekly, not compounded daily, not compounded hourly, minutely, secondly, but if it was always compounding, you would have an infinitely small percentage rate, but being compounded in infinitely large number of times. And guess you would end up with? You would end up with $2 and rounding up to 72 cents. So this number ends up having applications to compound or exponential growth, but basing it in terms of E instead of in terms of the equation that we had earlier. And there are some benefits to it that we'll get into later. It involves natural logarithms and how that allows us to work and to solve for some information a little bit more easily. But here we have exponential growth, in terms of E. And what we have is we have n equals n sub 0 times E to the kt, where k is growth rate and t is number of time intervals of I'll say of growth. Same as we talked about before, where the t is using the same units that k are. So if we have a monthly growth rate, and then t then would be number of months. This allows us to calculate exponential growth. That if you took the same data and you calculate exponential growth here with this formula, and you calculated the same exponential growth using your formula from lesson two, right? Yeah, you get slightly different values. And just what happens is sometimes one equation is a slightly better fit for the situation than the other. What usually happens is this, is the mathematician will take data points and then they'll plug the data points into like this equation, and they'll plug the data points into the other equation, for like the lesson 2 equation, and then they'll see which one fits the data better, which equation will give a better prediction of a later data point that they measure. And then based on which equation fits the data better, then they'll go with that, and that's what they'll use as the basis of their model. But again, this using E will make some certain stuff simpler a little bit later on. So that is exponential growth or decay in terms of E. And then one more equation, which would be continuously compounding interest, which I've never seen anywhere. But the idea of it is valid, and we can calculate it. And all it does is, so this would be continuously compounded interest, and we have A equals PE to the RT. Or same as before, R is your rate of growth, T is the time interval that the rate of growth is based on. Yeah, so this lesson you have a couple word problems, and I think that's about it. This is more just introducing the idea of E, showing how it can be used with some formulas that are calculating similar things that you did with your regular exponential growth formulas from lesson 2. And let me know if you have any questions. Let's see, do I want to go into... Well, sure. Let me just give one little example of where the number E shows up. There's something called the catenary curve. Catenary curve. This comes up in number 10 of the homework a little bit. If you graph y equals e to the x plus e to the negative x over 2, you get something that looks almost like a parabola. Looks almost like a parabola. Let's see. So if x is 0, e to this, that's 1 plus 1. Yeah, so it crosses at 1. Almost looks like a parabola. The shape is just a little bit different. I'm not good enough at drawing the shapes to get the difference. But this shape that is modeled with this equation shows up all over the place. In particular, if you took something like a rope or like a jump rope or a cable and you dangled it between two people. Let's just say you have two people here, and another person here, and they're each hanging on to a rope, and the rope is dangling between them. Guess what shape you get? You get this shape that is modeled by this equation. Now, if you took that same catenary curve that is dangled between them, the catenary curve, by the way, there are things called hyperbolic trig functions that we won't get into in this course. Like cosh is what's called this hyperbolic cosine that is also based on this equation. That's also something different, but just FYI if you wanted to look up anything more about it. If you took this catenary curve and you dangled weights from it, evenly spaced, and the same amount of weight in each case, now it is bearing a load. And if it is bearing a load, the shape deforms a little bit and it becomes nature's load-bearing shape, and it would go from a catenary curve, catenary, to a parabola. The shape would deform to become a parabola. So basically this equation, if you dangle weights from it, it ends up turning into just that equation. And yeah, anyway, so just one more example of how this number E shows up all over the place in nature. And we'll see that's later, that's why logarithms that have E as the base are called natural logarithms, because they show up in nature so much. Anyway, I'll shoot you, when I email these, I'll let you know what problems to do and what problems you don't need to do to simplify things a little bit. And we will go from there. All right, hope that makes sense. As always, let me know if you have any questions.